Okay, YouTube, this is my first video in which we're going to be constructing what we call rose curves in the polar coordinate system. And we're essentially talking about a classification of equations that have graphs that their properties basically can be inferred from their equations here that are each of the form a cosine n theta and a sine n theta. So essentially we have a cosine-based graph, a sine-based graph, and what I want to do is I want to kind of explore the values of a and the values of n here and kind of look at how they affect the graph before we kind of talk about how we could build these graphs from scratch. So when we go over here to Desmos, what I want everybody to look at here is that we have the equation r equals a cosine n theta, which I'm going to start with our cosine based graph here, and you'll notice that our a value is 4 at the moment, so we'd have 4 cosine, and we'd really have theta because n has a value of 1 at the moment. But what you'll see here is we get our circular graph that is very cosine based. Recall that cosine-based graphs, if we have a function of cosine, then it'll be symmetrical. I guess we could write that down here. Symmetrical about the horizontal axis. Okay, and if we have sine-based graphs, we're going to look at this here. We say symmetry about the vertical axis. But this is very true with all of our graphs that are cosine and sine based respectively. But what I want to do is I want to open up the door for n being different. Now I've observed a before. A has a direct relationship between the maximum value r ever gets. In this case, if a is 4, r, the biggest r we'll ever get on this graph, is out to 4. And we say, I want to point this out here, the maximum value of r is always the absolute value of a. Okay, so I suppose we could make a note of that as well. So we would say that max r value is at the absolute value of a. We should just say is equal to the absolute value of a. So we could say that is very, very much true here as well. Okay. When we look at the value of n, let's go take a look at the value of n here. When we say n theta, you notice that n is equal to 1 here, and I have my sine graph up here as well. As a matter of fact, I put both of them in there. We're just looking at the cosine, but you see our two circles here. The moment we look at n being bigger than 1, all of a sudden we change the shape of our graph fundamentally, and this is where they get their name, these rose curves here. And essentially what's happening is we get a number of petals, is what we call them, okay? So I will say this about all of our petals: they're always going to be evenly spaced apart. So that is to say, if we had, for instance, 4 petals, I would say, well, what's the rotation between each one? Well, we'd say 90 degrees or pi halves. Well, that's because if you took 2 pi, which is full rotation, divided it 4 ways, you would get 2 pi fourths, which is pi halves. Okay, so we get 4 petals here when n is equal to 2. Well, what I want to do is come up with a generalization. What if n is equal to 3? We get 3 petals. So let's see, we have 1 petal at 1, 4 petals at 2, 3 petals at 3, looks like 8 petals at 4, 5 petals at 5, let's see, 1, 2, 3, 12 petals at 6. What we're noticing here is that the number of petals is directly related to this n value here. And I'm noticing that every time n is odd, that value of n is actually equal to the number of petals this has. But if you notice carefully here, n is 8. This should have 16 petals. And the reason why is because whenever n is even, then it's going to have 2 times that amount in petals. Okay, so we'll put it this way. We say n value about both of these here. If n odd, then we say n petals is what we would say about our picture here in general. And we say if n is even, then we're going to have 2 times that amount in the number of petals here. Okay, so going back and looking at our graph, basically we could sit around and we could play with the number of petals. We could say if this were 5, I would predict it has 5 petals. Some things I want to notice about this are 3.4 is our maximum r value here. You notice that it goes out to 3.4 on my graph. I don't think I can give you a coordinate pair here, but this does look like it goes out to 3 and then 4/10 of the way to 4 here. And then other things, this is cosine based. So what you'll notice here is that this graph, it is symmetrical about this horizontal axis. So one thing I want to kind of point out along with this symmetry here about the polar axis is that cosine graphs, their petals always start on the horizontal axis. So it's going to start way out here at 3, and then it's going to go do its thing, okay? So what we're going to do here is we're going to make a note here with at least cosine graphs, and I'll switch colors here. But we say that these start at the polar axis. Start on the polar axis. This is the horizontal axis, okay? They will start there. Whereas we say that traditionally sine graphs, now we haven't really looked at the sine graph here, What if I were to turn on the sine graph here? You notice that they have the same number of petals, by the way. Their rotations are a little bit off here, but you see A affects them the same way. A affects them the same way with reflections. You know, it opens downward, opens upward. N, the number of petals, is kind of hard to see there, but if we said 3 petals, they both have 3. They both have 4 if N is 2. But essentially, you know, when you look at the sine graph, we say that the sine graph here, it has symmetry about this y-axis. So it's always going to start at what we call the pole, which is a weird thing to say because the pole is the origin. How does it start at the origin? But it just does. So we say starts at the origin, or we call this the pole. So essentially what I can tell you is often what we're going to do when we try to graph sine graphs here is we're going to try to figure out what is the angle at which the first petal is facing, because I notice here that this petal goes out and it looks like, you know, 4.25 or 4.5 in a pi 6 direction. I would know that since it has 3 petals, I could find out how far spaced apart each of the 3 petals are by taking 2 pi and splitting it up by 3. So 2 pi thirds, if I were to add a 2 pi thirds rotation on the pi 6th here, I would rotate over to the next petal. So I'll share with you a way to figure out which way the first petal goes here. But what I want to do is basically use all these observations now to say what is it that we could figure out about this r equals 4 sine 2 theta graph. So I want you to kind of challenge yourself to think about this here in terms of what shape this is. I'm going to share this with you here. We say it's just a rose curve. Well, these are all going to be rose curves. But we say the number of petals here, basically. So we say rose curve with how many petals? Well, I notice that n is even. So if n is even, we're going to have 2 times that amount in petals. So if n is 2 here, you guys, we're going to have 4 petals. So we have a 4-petaled rose curve here. We say it's a sine curve. So in terms of symmetry, I do want to write a note down here. Symmetry about the vertical axis, since it's a sine curve. Okay, it's going to start at the pole but have symmetry about the vertical axis. We say what's the maximum r value? Well, if 4 is our a value here in sine, the biggest or smallest it ever gets is -1 and 1. You know, then we'd say that 4 is going to be our maximum r value here, the absolute value of 4. The number of zeros. Now we want to go search for these zeros. So again, when you find zeros, we're going to go ahead and plug 0 in for r. We're going to say I know that r equals 0. What are the angles that give me zeros? And there can be more than one. But we say 4 sine 2 theta. So I'm going to divide both sides by 4 here. I get sine 2 theta equals 0. And if we take the sine inverse of both sides, what we basically end up with here is 2 theta is equal to the sine inverse of 0. So we say, well, where is sine on the unit circle equal to 0? I've got a few points here. But the thing I want to point out is essentially this. Because we have 4 petals, okay, 4 petals. I want you to think about this here. It's going to go out from the origin, come back, go back out from the origin, come back, go back out from the origin, come back, go back out from the origin, come back, okay? So it's going to have started at 0 at the pole and then come around back to 0 like 4 times. So we're going to have like 5 zeros here. What I basically want to do is I want to say if it's a sine curve, then whatever, you know, number of petals you have, the number of zeros is petals plus 1. If sine, okay? So when I say this here, I say I notice that I have 4 petals. I'm going to say that it has 5 zeros, and we're going to find them all. So this means that we're going to have to list 5 of these ordered pairs here, or 5 values here. But we say 0 and pi usually, or what we say that we have these zeros here. I'm going to say that 2 theta in this case is equal to 0, okay? But it's also equal to pi. I'm going to keep going. 2 pi, 3 pi, and 4 pi. I want to make sure I get all of my zeros. And we're going to split all of these 2 ways. So if we split them all 2 ways, what we find out is I'm going to write them in a little bit different order here. We get 0 over 2, which is 0, pi over 2, which is pi halves, 2 pi over 2, which is pi, 3 pi over 2, which is another 0 there, and we say at 4 pi over 2 or 2 pi, these are all 5 of our zeros here. And forgive me, but you know, you should be writing them right here. So if we were to put these on the graph, what I want you to understand is that this graph is just a rose curve that just kind of repeats its behavior, and we could figure out the rest from what we know about the basic characteristics. So in terms of listing these in, you know, I always say start at 0 with your angle, and we notice that 0 is one of our zeros here, no pun intended. And I would say, well, what's my next 0? My next 0 is like pi halves. Oops, that's an angle, so we should put it in the angles row. So between these, I say, like if I were to plug in pi force here, you know, just to get between these 2 zeros, if you plugged in pi force, we would get r equals 4 sine of 2 times pi force. 2 pi force is really a pi halves, and the sine value of pi halves is 1. So we would get sine is 1 here, and we get 4. So basically, we would say that we know some points here, and I'm going to go ahead and put these on the graph at 0, we're at 0, okay? At pi fourths, we're at 4. And then at pi halves, we're back at 0. So basically what just happened is it did this. And it came back. Okay, so here's our first petal. If I said we had 4 petals, one could already kind of assume that, if they're all going to be evenly spaced apart, they're probably going to lie along these angles right here, if you can imagine this already as existing, okay? But there are a few things I do want to say about how I would figure that out, and also where our first petal started here. We would say if it's a sine curve, this is not going to be true in the next video here with the cosine, but if sine rose, then what we're going to do is this. Set this part right here, okay? Set equal to 1. We are going to set the sine of 2 theta equal to 1. And basically what I know is this. I know that it'll reach its maximum petal distance here at its first petal at some angle theta. So I already know that I want this to have a maximum value, and it's only going to have a maximum value if this right here has a value of 1, let alone the fact that it's going to have a maximum value of 4. I just say that, well, sine 2 theta would have to equal 1 in the first place. So with sine curves, we often do this, and what you know is that sine is always equal to 1 at pi halves anyways. So this is going to be a common response here, but we say 2 times theta, or 2 times our argument here would be pi halves, and if we divide both sides by that, we say pi fourths. So if you had not wanted to list just 2 of your zeros here, and then list an in-between value, and then infer the rest, we could say you set your sine value equal to 1 and solve for the angle, and look what we found out. We found out that at pi fourths, which we already kind of deduced here, that we have our first angle. This is not always going to be symmetrical like this, so we do need to know how to find this. So I'm going to go ahead and put the rest of this together. I know that a full rotation is 2 pi, and if I have 4 petals, each one is going to have a pi halves rotation. So pi halves rotated from here. It's also going to be back at 4, as we said. Pi halves from here, pi, will be out at 4, and pi halves from here out at 4. Basically, here would be our rose curve right here. And it's not my best rose curve ever, but this is what we would see. So in the next video, we'll look at a cosine graph, and we'll talk about how you piece it together. Cheers.